Okay, is the mic working? Twinkle, twinkle, little star, wave your hands there where you are. Okay, yeah, good. All right, so two quick things about the charged particle on the ring around the solenoid. I'll try to keep it brief. So it's quite interesting to think about computing amplitudes in this theory, and it's completely solvable, so let's do that. So for simplicity, let's set h bar equal to 1, and then let's consider the matrix element. This is the Euclidean time propagation. H is the Hamiltonian, beta is the Euclidean time. We diagonalized, and we called it h sub b. And we diagonalized h sub b last time, so just sticking in a complete set of eigenstates, you automatically get this. Plus I m phi 1 minus phi 2. I stressed last time that we have periodicity in B. And notice that that's manifest here because if I shift b by 1, then I can compensate by shifting the integer m by 1. On the other hand, if you look in books like Feynman and Higgs, you can see that these kinds of Euclidean propagation amplitudes can also be given a path integral point expression. So I'll call this z of phi 2, phi 1, beta. And so this is the Euclidean path integral with boundary conditions that phi of 0 is phi 1 and phi of beta is phi 2. And we have the Wick rotated action. So we have e to the minus Wick rotated action. So that's an integral from 0 to beta of 1/2 I phi dot squared plus I b phi dot. Here's our theta term that we discussed last term. Now this path integral is quadratic, so the semi-classical, this is quadratic, so the semi-classical approximation is exact. So that means we're going to sum over the accessible solutions of the Euclidean equations of motion and multiply by a one-loop determinant. All right. Remember, this doesn't affect the equations of motion, so altogether now, what's the equation of motion? Oh, come on. The equation of motion is phi double dot equals 0. Okay, let's see if you can do better with part B. What's the solutions of the equations of motion? Phi is AT plus B. Do we agree with that? I don't agree. Phi is only defined modulo 2 pi. So if we were doing physics 101, you would be right. You would write phi is phi 1. You'd solve your boundary conditions. Phi 2 minus phi 1 over beta times t. Put a t over there. But that's not right because phi is only defined modulo 2 pi. So I can also have 2 pi w, where w is an integer. In other words, as I progress from time 0 to beta, this phi winds around the circle. Phi w times, starting from phi 1, ending up at phi 2. Okay, so those are the solutions of the equations of motion. Remember, the real field, the actual field here is e to the I phi of t. That's the only thing that has to be single valued and so on. So, all right, so now you plug that into the Euclidean action, and you do a one-loop determinant by zeta function regularization. I won't go through the details. It's in my group theory notes if you want to see all details. And so you get a sum over the classical solutions of minus 2 pi squared over beta of w plus phi 2 minus phi 1 over 2 pi squared minus 2 pi I b w plus phi 2 minus phi 1 over 2 pi. Okay, so that's a little, this part is an easy exercise for you to plug in that solutions of the equations of motion and get that. Now, there's something very remarkable here. Look at the two expressions on the blackboard. The one on top with the sum over m and the one over here with the sum over w. These are the same, right? Because I'm computing the same physical quantity just in two different ways. Up there, I just substituted a complete set of eigenvectors of the Hamiltonian, and here I did a path integral. But they don't look very much the same. You see, the sum on top, we have a sum of terms exponentially convergent for beta goes to plus infinity, and the bottom is we have a sum of terms for exponentially convergent for beta goes to 0. We have 1 over beta here. We have beta up there. So it seems kind of remarkable that these are the same. Well, the mathematical reason, I mean, physically they're the same because it's the same quantity. But the mathematical reason why they're actually the same is that both are special cases of what's called Riemann's theta function with characteristics, which is defined as follows. And theta functions play a big role in discussing the spaces of states in Chern-Simons theory. So no, I haven't forgotten that I'm talking about Chern-Simons. So we have a sum over n and z, e to the I pi tau n plus theta squared plus 2 pi I n plus theta z plus phi. All right, so that's a definition. Now, this is a holomorphic function for tau and absolutely convergent. Holomorphic function of tau for tau in the upper half plane. And it's an entire function for z. Actually, it's the analyticity in tau is interesting. This is an example of an analytic function with what's called a natural boundary. So you can define this as a nice analytic function in the upper half plane, but you cannot analytically continue through the real axis because there's a dense set of singularities along the real axis. Anyway, using the Poisson, both sums here are special cases of Riemann's theta function, and that's another exercise. Figure out what tau and phi and theta would have to be in these two cases. And now this theta function satisfies a beautiful identity, minus z over tau, called the modular identity, is minus I tau to the 1/2. That's the principal value of the square root. It makes sense because you see the real part is positive because the imaginary part of tau is positive. This is e to the 2 pi I theta phi, e to the I pi z squared over tau, theta, and now the characteristics get flipped. We have z and tau. And so you can prove this using what's called the Poisson summation formula. Okay? The Poisson summation formula says that a sum of plane waves is a periodic sum of delta functions. Okay, so that's another exercise. And so now another exercise that comes right out of this is let's suppose that 2b is odd. Remember, I drew a strong distinction between the case where 2b is an integer, 2b is even, and 2b is odd. Supposing 2b is odd, show that for beta goes to plus infinity, phi 2 e to the minus beta h phi 1 is 2 e to the I over 2 phi 1 minus phi 2 cosine of phi 1 minus phi 2 over 2 e to the minus beta times the ground state energy times 1 plus exponentially small. All right? And when you show that, then you realize there's a little puzzle. I stressed last time that we have parity or charge conjugation, depending on your point of view, that takes phi goes to minus phi. And that's a symmetry, even quantum mechanically, when 2b is odd. In fact, the true symmetry was a central extension of O of 2 called pin plus of 2. That's where we ended. But now you should be puzzled, because the right-hand side of this equation is not invariant under phi goes to minus phi. So that's homework. Okay. What's going on there? Okay. All right. So the second remark I want to make about the particle on the ring is about gauging the SO2 global symmetry. So let me make a very general remark first, since I'm on the topic of gauging a global symmetry. If you have a theory T, so this is a theory with a G symmetry, then you can gauge it. Now, gauging is a two-step process. So gauging. It's a little bit ambiguous to say gauge it. It's a two-step process. One is you make the theory equivariant, make T equivariant by coupling to external G gauge fields. So you couple the currents. If it has a G symmetry, if a G is a continuous group, it has a Noether currents. You couple the gauge fields to the G gauge fields. And secondly, then you sum over gauge and equivalent external gauge fields, G gauge fields. Now, it makes a lot of sense to do one and not two. And if you do one, then you can probe all sorts of interesting things about the theory, like anomalies, for example. So I want to say this for the benefit of those who know something about the more geometric formulation of field theory using functors from Bohrism categories. So this is really a remark for those who already know something about this. This is rather vague, actually, because what do you do when G is a finite group? Well, a nice point of view is that if you view field theory as a functor, so those of you who don't know what I'm talking about, just bear with me. We'll get back to simpler things in a moment. So as a functor from the Bohrism category of, let's say, an n-dimensional field theory, from the Bourdism category of n minus 1 manifolds as objects and n manifolds as n-dimensional Bourdisms as morphisms. We give this some structure, orientation, spin structure, Riemannian metric, whatever you like. And it's a functor to some target category. It has to be a tensor category. Okay, what is gauging? Well, first of all, it makes sense to talk about this having a G symmetry. And then what is step one? It's replacing F by what I'll call F equivariant, where the only thing is we're changing the structure by adding a new structure. Principal G bundles with connection. Okay? So that's gauging. And then 2 is summing over isomorphism classes of principal G bundles with connections. So that's the real story. Now, in our case, we're doing something very, very simple with our, back to our quantum mechanics problem. What we just do is we take this SO question. Yes?
Just a quick question. How does this relate to the symmetries of the original theory we start with when we gauge them?
So, yeah. So, the question is, how does this relate, if I understand it correctly, to the theories of the to the symmetries of the theory? Well, okay, so gauging is all, yeah, so that's a good point. So F equivariant is not unique. You can couple to external gauge fields in many ways. You could add gauge invariant operators of the external gauge fields. So if you have a symmetry, though, what you can do is you could say, okay, so I now want to take this and I want to consider a principal G bundle, and I want to define something which reduces to F with the trivial bundle with the trivial connection, and yet makes geometric sense. And I don't think I can say anything more general than that.
Is it always possible, or is that unique, or is that many options?
It's always possible if I consider principal G bundles with connection. There might be an obstruction if I want it to be only depend on the isomorphism class of the connection, and that would be an anomaly. That's a very good way of thinking about what an anomaly is. Okay, so back to quantum mechanics, unless there are other questions.
The reason why you define the field theory using the Bourdism is to relate your theory to anomaly, or to symmetry?
No, it's to make this what, right. Did I introduce this fancy way of saying things because I wanted to talk about anomalies? The answer is no. I wanted to express it in a way that makes sense for any group G. Okay?
What's the problem if you just consider the category of manifolds?
I didn't hear that question.
What is the problem if you define your field theory only using manifolds?
Well, but then, I mean, I'm describing a procedure of gauging a G symmetry. So the question was, what was the question? Why am I not just using the Bourdism category of manifolds? Well, because that's not what I want to do. I want to say what it means to gauge a G symmetry. All right. So let's go back to the quantum mechanics. So we had this global symmetry where we just shift phi of t by a constant rotation. So G equals e to the I alpha is an nu1. And now what does it mean to make it equivariant? Well, we allow this alpha to depend on time, and we introduce an external gauge field, that's what the E is for, which shifts by a E plus I G inverse of t now, d sub t, g of t. Okay? And let me stress that this is not the Maxwell field. We already used Maxwell to produce our solenoid. This is some kind of rotational gauge field. All right, so then the Euclidean action would be 1/2 I phi dot plus AE squared plus IB phi dot plus A E sub t dt. Notice that in Euclidean space, I should have mentioned that before, in Euclidean space, the theta term remains pure imaginary. Okay, now periodicity in B, so I remind you that theta 2B was theta over pi. So periodicity, integer periodicity in B is 2 pi periodicity in theta. That's a good thing, and now we've clearly lost it. It didn't matter before because classically, or even quantum mechanically, because this is a total derivative. But over here now we have this term, and that spoils periodicity in B. But we can restore it if we want it partially by replacing. So this is S Euclidean by replacing e to the minus S Euclidean by adding a one-dimensional Chern-Simons term with some constant k, and it should be manifest that the theory now with b and k is equal to the theory with b plus 1 and k plus 1. Okay. So that's my motivation for thinking about this one-dimensional Chern-Simons term. But now we have a very important question to ask. We want to ask, is this thing gauge invariant? Gauge invariant under this gauge transformation g of t equals e to the I alpha of t. It's not obvious because we see an explicit gauge field. It's not hidden in any field strength. So is this gauge invariant or not? Well, under a gauge transformation, e to the I k, integral from t1 to t2, a sub t e of dt, goes to e to the minus I. This was in Tom's talk yesterday. E to the I k, t1 to t2, ate. He had a much more sophisticated version, but nevertheless, this is how it transforms. Just depends on the gauge transformation at the endpoints. Now, is this gauge invariant or not? Well, it depends on all sorts of things that you have to specify in your problem. So if, for example, we're working on RT and we have boundary conditions that the gauge transformation goes to 1 at infinity, well, yes, it's gauge invariant. If the gauge group, G external, is R, not U1, then yes, it's gauge invariant even on a Euclidean circle. Because if the gauge group is R, then okay, so if I'm now let's suppose I'm working on a Euclidean circle. So what I've got is I've got to make sense of the integral of e to the I k, integral over that circle of a sub t e dt. Okay? This I would take t to be 0, t1 to be 0, and t2 to be beta, say, if I'm using periodicity with period length beta. But then these would cancel because if my gauge group were R, they would have to be equal. But if my external gauge group is U1 and I'm working on the circle, then you see alpha of t plus beta can be alpha of t plus 2 pi w, where w is an integer. Because only e to the I alpha of t has to be periodic. But then this change here, so this goes to the same thing, times e to the I 2 pi w times k. So it picks up this factor. This had better be equal to 1. And so that implies that k is an integer. Okay? That's the prototypical argument for the quantization of a Chern-Simons term. We have this explicit A dependence in this term in the action. We want the exponentiated, the action is not invariant, but we want the exponentiated action to be invariant, and that quantizes k. This is the simplest example of that. Now, there's another way in which you could try and define this to be gauge invariant. Which again involves these kinds of Bohrism and ideas. So another way, a very often used way to define Chern-Simons terms e to the I k integral a external sub t dt around this circle is the following. Imagine that you take your circle and imagine that it's the boundary of some two-dimensional surface. So here's S1 sub t. So the boundary of this two-dimensional surface is S1 sub t. And imagine that we could extend the gauge field into the rest of the surface. And for those of you who know what a principal U1 bundle is, you have to extend the principal U1 bundle into the rest of the surface and extend the gauge field. In this case, there's no obstruction. In general, with such extension questions, there can be topological obstructions, but not here. Okay, then you could say, okay, I define this as the integral of I k, the integral of f, integrated over sigma. And that's manifestly a sensible thing to try because of Stokes' theorem. F is locally dA. Stokes' theorem, read backwards, gives you back this. But now, this is nice because F is gauge invariant. Okay. But, there's a price you had to pay. You had to make a choice of sigma. Okay? So if you made two different choices of sigma, you might get different answers. And so it would actually depend on the higher dimensional theory, which is, from this point of view, what I'm doing right now, fictitious. So the extension is independent of sigma only if k is an integer. Because, as I'll discuss in a moment, again, but let me say it now, f is with my conventions, is a closed two form with 2 pi integral periods. So if I have another extension, then the difference would be the integral over the closed manifold, and the integral of f over a closed manifold is 2 pi times an integer. That's because f over 2 pi represents a first Chern class. Okay, so that's again a kind of standard story in Chern-Simons theory. Now, I want to give you a little puzzle here. Another homework problem. Supposing I don't care about the fact that, supposing I don't care about which sigma, I don't care about independence from sigma. I choose a sigma. Let me choose a sigma. Okay? I choose a sigma whose boundary is S1. And now I simply define this side to be that. The right-hand side is manifestly gauge invariant because f is gauge invariant. But now's the puzzle. That's true for any value of k. K could be any real number. You see, this expression, if I choose a sigma, makes sense for any value of k and is gauge invariant. But I just argued that this is only gauge invariant when k is an integer. So, resolve the puzzle. That's the puzzle. Okay, now let's get back to Chern-Simons theories. Enough on the quantum mechanics. So before diving into a particular example of Chern-Simons theory, I want to make one more point. Again, sort of a general overview, bird's eye point of view type of thing, which is, what's the data I need to define a Chern-Simons theory? What data goes into a Chern-Simons theory? And really, it's amazing. There's only two pieces of data. One is a Lie group, G, and the other is what's called a level. So topology gives us a machine. Topology gives us a machine that takes to any Lie group, assigns it a finitely generated abelian group, which has this fancy name. Now, I'm not going to try and define it. You can ask me afterwards if you want. So it's just some finitely generated abelian group. That's where the level lives. So the level is K, which lives in here. That's where K really lives. And it has to satisfy a non-degeneracy condition. Degeneracy condition. And then what do my amplitudes depend on? Well, M3 has to be oriented. And there's something called a P1 structure. So there's a fancy bit of topological data that people usually don't talk about. And the line defects become ribbons. And we'll see that in the U1 case. We'll discuss that in detail. Now, at this level, the theory is best developed for G compact. So let me say a general word about compact Lie groups. What does the general compact Lie group look like? Well, if somebody gives you a compact Lie group, the first thing you should ask is, what is the space of connected components? Okay, so the Lie group is a manifold, so it has a topology, so it has a space of connected components. And there's one distinguished component, which is the connected component with the identity. Okay, and it's not hard to show that this is a normal subgroup of G. Because it's a normal subgroup, G mod G1 is a group, and this is isomorphic to the set of connected components. So in this case, the set of connected components has a group structure. So this can be any finite group. Has to be finite because we're talking about compact groups. A finite group is an example of a zero-dimensional Lie group. Therefore, pi naught can be any finite group. Now, what does G1 look like? Well, G1, you can show, always looks like what I'll call G1 semi-simple times a torus divided by Z. Z is a subgroup of the center and is a finite abelian group. Okay? And what does G1 semi-simple look like? Well, it's the product of what are called simple groups. And the simple groups were classified by Cartan. And he has a classification A through G. Okay, so that's what the general compact Lie group looks like. And so Chern-Simons theory, together with a level, makes sense for all of those. Okay.
What is H4 again? Homology or
H4 is the cohomology with coefficients in Z. And if you want to know what BG is, ask me later. Okay. All right. So after all this grand stuff, we're going to descend just to g equals u1. Okay? And h4 of bu1, well, in this case, I could tell you what bg is. It's Cp infinity with z, and that's isomorphic to z. So a level is just an integer, and non-degeneracy means it's not 0. I explained the conventions for gauge transformations for u1 last time, and so A gauge transformed by G is A minus I G inverse dg, where G is a function from our three manifold into u1. And now I want to make a distinction between small and large gauge transformations. So small gauge transformations are those for which I can take a logarithm. So g of x equals e to the I epsilon of x, and epsilon of x is a single valued function, real valued function on M3. Large gauge transformations are those for which there exists a loop in M3 so that the period around the loop, which is by definition the integral of g inverse dg around the loop, is not 0. If the periods around all the closed loops are 0, then you can show that there exists a logarithm. Okay. Now, another way of saying this is that we're shifting A goes to A plus omega, where omega is a closed one form with 2 pi times z periods. So these periods of g inverse dg are always 2 pi times an integer. All right, so now we're ready to look at the gauge invariance of the U1 Chern-Simons term. So let's consider exponential of I times kappa over 2 pi, integral over our oriented three manifold A f. And remember, f is dA. So again, let's ask about gauge invariance. It's just like the discussion over there. AF under a gauge transformation goes to AF plus omega times f. So this has 2 pi integral periods. And now with my normalization, this has 2 pi integral periods. That is to say, the integral of f around any closed 2 cycle is in 2 pi times z. So f over 2 pi is what's called a Chern-Weil representative of the first Chern class of whatever line bundle I'm using, or whatever U1 principal bundle I'm using to put my connection on. All right, so the integral over the three manifold is going to be 4 pi squared times an integer. And so that implies, so gauge invariant, if and only if kappa is in z. Because there always exists a three manifold and a principal U1 bundle over the three manifold, so that I can get A times f is in 2 pi squared times any integer. So if you give me an integer, I'll find a bundle and a connection and an M3, so I get 2 pi squared times that integer, and therefore I really have to have kappa times z. You see, it could have been that my statement here is compatible with the possibility, you could have asked me, well, could it happen that the integral of A times f is always 2 pi squared times an even integer? Well, then I would have a finer classification, right? If it had happened that I always got an even integer, then I could have taken kappa to be a half integer and I would have had gauge invariance. But the statement is, in fact, I can get any integer. And that's what really forces kappa to be an integer for gauge invariance. Okay, good. Any questions about that? All right, so we're eventually going to look at a quantum field theory with that as the action principle. But that's a little exotic. So let's start with a more natural three-dimensional gauge theory action. I shouldn't say natural, a more common, more familiar action principle. Let's start with Maxwell theory. So the Lorentzian action is e to the I, and I'll just choose my normalization of the coupling constant, so it's f star f. And in Euclidean space, it'll look like e to the minus the integral of 1 over 8 pi squared, e squared f star f. So that's Maxwell theory. Okay, and now what we can do is we can add ADA, the Chern-Simons term. And we just saw that we can only do that when kappa is an integer. Similarly, when we rotate, Wick rotate to Euclidean signature, we're going to get the integral ADA here. All right, so these terms here, these depend on a metric. And not on orientation. These are independent of metric and depend on orientation. All right. So now let's investigate the physics of this theory a little bit. So let's consider 2 plus 1-dimensional Minkowski space with the Minkowskian metric. And you work out the equations of motion, and I hope I did it right. No guarantees there. So, I mean, the only thing that would be wrong is the 2's and pi's in the first term. But I think it should be d star f minus m times f equals 0, where m is 4 pi k e squared. So in 2 plus 1 dimensions, the electromagnetic coupling constant squared has the units of mass. All right, so now let's look at plane wave solutions. So we take a sub I goes from 1 to 0 to 2, and there's a polarization. We have e to the I p dot x, and you plug it in, and you get a lot of equations, which you find in the notes. And those equations lead to a dispersion relation, which is p0 squared, 0 is time, p0 squared minus vector squared minus m squared equals 0. And so what we see is that there are going to be two kinds of solutions. This is going to be 0 or this is going to be 0. Okay? When this is 0, we have the dispersion relation of a massive scalar. When p0 is 0, you plug it back into the rest of the solution, the equations of motion, and what you find is that f(1,2) of p is 0. In other words, f is a flat gauge field. So the solutions of the equations of motion factorize. There's a space of flat solutions and non-flat. This describes the degrees of freedom of a massive scalar particle in 2 plus 1 dimensions, as shown in detail by Desert, Jakiv, and Templeton in 1982. So now let's think a little bit about correlation functions in this theory. And what could we look at? Well, we could look at all sorts of things. We could look, for example, at f mu1 nu1 of x1, f mu n nu n of xn. Or we could look at these line defect vevs. And in this theory, these are going to be complicated functions of the x's, and they're going to depend in great detail on the actual loop. So if I take one loop and I deform it a little bit, I'm going to get a different correlation function. So these are going to be very non-trivial functions of loops and positions. But let's notice something. I said here we have metric dependence. Let's write out that metric dependence a little more. So we have 1 over e squared. We have d3x. We have the square root of the determinant of g. And then we have upper g mu nu, u1 nu 1, g upper mu 2 nu 2, f mu 1 mu 2, f nu 1 nu 2. All right. Supposing I start looking at longer and longer distance scales. So I take g mu nu goes to omega squared g mu nu. And omega, for what I'm doing, it's going to be a constant, unlike in Slava's talks and Xi's talks. So omega is just a constant. I'm just rescaling distances by a factor of omega. So what happens? What happens is volumes scale by omega cubed. Omega is positive. And this scales by 1 over omega to the 4th. So scaling distances by a factor of omega is equivalent to scaling the coupling constant by a factor of omega. So going to long distance is going to strong coupling. But the particle has a mass which is proportional to e squared. So this implies that if omega goes to infinity, the mass goes to infinity. So then the mass can't propagate. Okay, so what we expect is that at large distances, large masses, these correlators should go like e to the minus absolute value of m times the minimum of the distances. And that goes to 0. So these correlators all go to 0. For these correlators, well, nothing can propagate from here to here. So we are expecting to get topological invariance. And that's the only thing that's going to remain, the topology of these loops. And as I stressed last time, these loops can link, and they can even be knotted. And I won't attempt to try and draw the trefoil again, because I'm sure I'll mess it up. OK, so now in this limit, the action degenerates to the pure Chern-Simons action. OK, so let me make a few remarks about that. So indeed, one, we get formal metric independence. Although it's very nice taking this point of view, you can see that actually for some quantities, like the partition function, taking e squared to infinity, there's some residual metric dependence in the partition function. But it's fortunately just local in the metric, and so we can get rid of it with a counter term. So that's an example of a topological anomaly. Another remark, another important remark, is that in the pure Chern-Simons theory, kappa functions like 1 over h bar. So kappa goes to infinity is the semi-classical limit. And finally, this theory is Gaussian. So there's no excuse. There's no excuse. You have to understand everything about this theory. All right. The first thing we want to understand about this theory, and unfortunately it will probably take us the rest of the lectures, is what is the space of states, of physical states, when space is a closed topological surface? So this is the key question I want to now turn to. let's take M3 to be sigma 2 times R. Okay, and again, G is just U1, although this should make sense for any compact Lie group. And, well, in this case, there should be a Hilbert space. Now, the theory depends on the orientation of M3, and orientation of M3 is equivalent to an orientation of M2, and there's a kappa. And so how do we describe this? What is this? Okay, so first remark. When I have a decomposition, a space-time decomposition like this, I could take my gauge field, and I can write it as A sub s plus A0 dx0, where x0 is this time direction. Okay, so now the action, AdA, looks like this. It's minus the integral dx0, the integral over sigma 2 of A spatial, d naught A spatial, minus the integral dx0 of the integral of A0 F spatial over sigma 2. So A0 does not appear with derivatives, and so this is functioning as a Lagrange multiplier. So that's forcing us to Fs equals 0, flat gauge fields. So we can hope flat gauge fields on sigma 2. So we can hope that, that the path integral is going to localize to the space of flat gauge fields on sigma 2. That's generalizing this little statement we found here just for plane waves in Minkowski space. Now, the other thing is, notice that this action is first order in time derivatives. And so again, I want to mention a general lesson you can learn from this. So general lesson. If you have an action which is first order in time derivatives, so this is just some general action, phi I are just some very general set of fields, okay, then you should interpret this, you should interpret the path integral is over paths, not in configuration space, but in phase space. In other words, we're talking about an integral, a path integral over the spaces of, if you like, P's and Q's, not just Q's. So oftentimes we write path integrals, we write second order actions and derivatives, and we're thinking of the integral over all paths the way Feynman did, the integral over the Q's. But you can also consider path integrals where you integrate over paths that go in phase space. So what is phase space? Well, mathematically, phase space, I'm going to use this term interchangeably, is a symplectic manifold. And what is a symplectic manifold? A symplectic manifold is a manifold, I'll call it P for phase space, with a two-form, omega, which is closed and non-degenerate. What that means is that if I look in local coordinates, omega ij, d phi I, d phi j, then this phi omega ij can depend on phi, but this is an anti-symmetric matrix, and this is always invertible. So that's what a phase space is. In fact, given an action which is first order in time derivatives, you can derive what the symplectic form is. You simply take a variation of the action under varying the fields, and you get di lambda j minus dj lambda I delta phi j d phi I dt. Well, there's your symplectic form right there. This is omega ij. So let's put that general remark to use in this example of U1 Chern-Simons. what do we learn? In the Chern-Simons theory, our phase space is equal to the space of all gauge fields on sigma 2. So sigma 2 is some topological surface with an orientation. Could have lots of holes. Just has to be closed. So that's very different from the symplectic structure you would get in Maxwell Chern-Simons. Here, because of the f star f, you would have second order inderivatives. Then a's are like the coordinates, and the symplectic structure is different. It's actually non-trivial and interesting to think about how one degenerates to the other. All right. So what we want to do, let me say this more mathematically. The phase space, P, for us, is equal to the space of all connections on principal U1 bundles, P over sigma 2. Over sigma 2, not over M3. We're talking about gauge fields on a two-dimensional surface. Okay, we got rid of the third direction by taking this Hamiltonian point of view. All right, so we want to quantize this phase space. So first question is, what does it even mean to quantize a phase space? Let's spend some time on that. You're too quiet. Yes, good.
What? We're going to ask for what?
Good question. The question was, did I mean flat gauge fields? Did I make a mistake? The answer is no. I did not make a mistake. We're integrating over, in our path integral, we're integrating over all gauge fields. Now, it's true that if we did the integral over A naught, we would localize to the space of flat gauge fields. And it is also true that eventually we're going to quantize the moduli space of flat gauge fields. That's our goal. But right now we haven't gotten there. We're going to start by quantizing the space of all gauge fields, not the flat ones. Any other questions? Okay, so another general thing. What does it mean to quantize a phase space, P and omega? That's a tricky question, actually. Well, one thing you might want it to mean is the following. You have a symplectic form, so now you define a family of symplectic forms by multiplying by k so that you can discuss a semi-classical limit. For each k, so let's take k to be an integer, but at this point it could have been a real number, but let's take it to be an integer. So for each k, we're going to have a Hilbert space of states. And then, here's the meat. For each function on phase space, so if f is a function, complex valued function on phase space, I'm supposed to get a linear operator of f, which is a C-linear operator on H sub k.
Don't you need a polarization?
No!
Can you repeat what you
Question, do I need a polarization? No. No. There are methods to quantize phase space. Some methods use polarizations. I do not need that. Now, what do we need? We need to put some conditions on this qk. So, 1, the limit as k goes to infinity of k times the operator norm of qk of f times qk of g minus qk of f times g should be less than infinity. So I put a k over there, so that means that this difference Okay, I can multiply functions on phase space. Those are just classical observables, if you like. Well, they're only observables if they're real. They're classical functions on phase space. I can multiply them. I can also multiply the operators. They might not agree, but they better agree for large K to order 1 over K. Similarly, the commutator of QK of F with QK of G should be minus I over K QK of the Poisson bracket of F and G. Here's where I'm using the symplectic structure, actually just the Poisson structure. Plus order 1 over K squared. And then finally, QK of F, well, it's an operator. I can take its adjoint if it's bounded for sure. If it's unbounded, I would have to worry about some functional analysis. But I take its adjoint, and then that's QK of F star. Now, as far as I'm aware, there's no universal procedure without introducing extra data of some kind for quantizing an absolutely general phase space. There exist formal procedures. And some names there are Fedosov. And I think the state of the art is a theorem by Kontsevich, which has a very nice physics interpretation by Cataneo and Felder in terms of a topological quantum mechanics kind of thing. And these give you formal series in 1 over K.
What do you say about the Hilbert spaces?
I'm just saying a list. The question was, could I say something about the Hilbert spaces? That is the thing you have to do. All I'm saying is there exist Hilbert spaces with, now Hilbert space isn't much, right? A Hilbert space, all Hilbert spaces are the same once you've said what the dimension is. The interesting thing is what is the operator algebra on the Hilbert spaces? That's the content of 1, 2, 3. So
in terms of like the functions on the phase space, or like the
no. All the meat is in the operator algebra. All Hilbert spaces are the same once you specify the dimension. Yeah.
Did you assume in the beginning that sigma 2 does not have boundary?
I think I said that. The question is, did I assume that sigma 2 does not have a boundary? And I don't know if I wrote it, but I said that sigma 2 is a closed manifold. It gets very interesting when we introduce a boundary. I said something about that yesterday. We get edge states, for example. Or if we have punctures, then we have these correspond to insertions of operators in the holographic correspondence to rational conformal field theory. But we're doing the simplest thing. We're taking a closed topological surface. Any other questions? Yes?
The Poisson bracket, that's just the form, the omega?
Sorry?
The Poisson bracket, that's...
The question is the Poisson bracket the form omega? Taken literally, the answer is no, but the answer is yes, because you define the Poisson bracket by inverting omega. So that's what the Poisson bracket is. Okay, so there are special cases where you have a nice polarization, where you know what to do. So if you have a global separation of Darboux coordinates, then you can do something. So if our phase space is of the form T star M, where M is Riemannian, notice I introduced some extra data right there, then I can form a Hilbert space which is L2 of M, and then I can take Pi to be minus I h bar is 1 over K, d by dq I, and so on. I might need to add a connection. And we'll use a variant of that, although M won't be Riemannian. The one that we're really interested in here is Kähler quantization. So let's suppose that P has a complex structure. Okay, so we have some tensor j mu nu of phi, and j squared is -1. And suppose that this complex structure is what's called compatible with the symplectic structure. So what that means is that, let me say it two ways. If you like indices, the way that it goes is you have omega mu nu. Okay, I think I was using ij. Let me switch to mu nu for this discussion. So I'm changing notation slightly. So omega mu nu of phi, and then we have j lambda mu of phi. Okay, so I can make this two-index tensor lambda nu tensor, and this should be symmetric. And I'm also going to ask that it be positive. So if you don't like indices, what I'm saying is that omega of j v1, j v2 is omega of v1, v2. And that implies that if I define g of v1, v2 to be omega of j v1, v2, that this is a positive symmetric form. That's what compatibility means. Okay, so I have a complex structure, and I have a compatible symplectic form, and what that means is I have a Kähler metric. So with the Kähler metric, with the complex structure, I can choose local complex coordinates, let's call them dzi, and then I can form the so-called Kähler form, which is I over 2 g I j bar, and that's what omega looks like. So that I is an index, and this I is the square root of -1. Okay, so that's one thing I'm assuming. I'm giving extra data. Notice I needed to assume that I have a complex structure. Now another piece of extra data is I have a holomorphic line bundle with a positive curvature. Okay, so if I have a section S of this, not necessarily holomorphic, then I have a Hermitian metric on my line bundle, H of S. And if I take d bar of log of H of S, multiply by I over 2 pi, this should be omega, our symplectic form. And so we can write omega as I over 2 pi d bar of k, and this is called the Kähler potential. So it's a locally defined real analytic function. So I'm giving myself all that data. Once I've given myself that data, I can go to town. So H sub k is by definition the holomorphic sections of the kth tensor power of L. And my inner product, I have to tell you what the inner product is. To make it a Hilbert space, it's the integral over P of e to the minus k times this Kähler potential, psi 1 star, psi 2, omega over 2 pi to the n over n factorial, where my real dimension of P is 2n. So the complex dimension is n. Now here I'm using a local trivialization of my line bundle, so I'm thinking of these as local holomorphic functions of z and z bar.
Why do you need a line bundle of holomorphic functions?
You will see in an example. So the question was, why do I need a line bundle? Great question. Why not just holomorphic functions? And I'm going to do two examples. I'm going to try and do two examples, and if I get to the second example, the answer to my question, to your question, will be clear. I mean, one answer is, well, I can do more. I mean, line bundles. sections of line bundles are nice generalizations of holomorphic functions. So if I can define such a thing for sections of line bundles, why not? It's an interesting generalization.
When you're in a situation where you both have to and want to these quantizations and both agree,
They will, in all examples I'm aware of, which includes Chern-Simons, the answer is yes. Sorry. The question, another good question. Supposing I have both structures 1 and 2 simultaneously, and I used both procedures, will I get compatible answers? It's a good question. As far as I'm aware, the answer is yes. There might be crazy counterexamples. I'm getting a little low on chalk in addition to time. Okay. Yeah, I should say one more thing here. I was just stressing how important it is to quantize the functions on phase space. So let me tell you what that is. So I'll tell you what it is by telling you what the matrix elements are. So this is equal to the integral e to the minus k, capital K, psi 1 star. I just put the function in. Now the function in general is not going to be holomorphic or anti-holomorphic, but I could put it in and do the integral. And then da-da-da-da. All right, so real quick, let's do 2 examples. OK, so the first example, let's take just good old R2 with its natural symplectic structure, dp wedge dq. OK? Now this is isomorphic to C, so we give it a complex structure. So omega over 2 pi is dp dq over 2 pi, really 2 pi h bar, but I've set h bar to 1 because I've already got the k. This is equal to I over 2 pi dz wedge dz bar. All right, so over the complex line, there's not too many things I can do with holomorphic line bundles. L is just going to literally be C times C. This is the base, that's the fiber. L tensor K is again going to be C times C. And so the holomorphic sections of L tensor K are going to be suitably normalizable holomorphic, entire functions on the complex plane. So in this case, I don't gain anything by using the word line bundle, but let's look at the inner product, psi 1, psi 2. Okay, so that's going to be e to the minus k. The Kähler form is just absolute value of z squared. I'm going to have psi 1 star, psi 2, omega over 2 pi. Right, so now we define the matrix elements of functions that way, and now I invite you as an exercise to define a dagger is the square root of k times the quantization of the function z, and a to be the square root of k times the quantization of the function z bar, and check that they satisfy the usual harmonic oscillator relations. So you naturally, so this is called the Bargmann representation. And it's a very nice way of dealing with questions with harmonic oscillators, in fact. Good for squeeze states and coherent states and things like that. OK, let's do example 2, which is important. OK, example 2. My phase space is going to be CP1, or if you don't know what that is, S2, with the volume form is a 2 form, and it's non-degenerate, and that's going to be our symplectic form. But we're going to stereographically project to the complex plane to make things easier. L over CP1 is going to be the Hopf line bundle with C1 of L equals +1. If you don't know what that is, it's the magnetic monopole bundle. It's the space where wave functions of an electron in the presence of a magnetic monopole, which is sitting inside this S2, that's where those wave functions are valued. Okay, so HK is the holomorphic sections of L tensor K. Okay, now I was asked by why introduce line bundles? You're about to see. Okay. All right, so let's look at psi 1, psi 2. Okay, so that's I over 2 pi e to the minus k times big K. Haven't told you what big K is yet. dz bar. Okay, here's the volume form on the sphere expressed after stereographic projection. And now K, well, you can work it out from the general formulas over there. I just told you what the volume form is, so now you solve omega equals dd bar capital K. And so what you'll discover is that this is I over 2 pi times the integral over the complex plane of psi 1 star psi 2 dz bar over 1 plus z squared to the k plus 2. I'm assuming k is positive. Well, you see, now I'm going to get a very different set of holomorphic functions which are normalizable depending on k. For example, 1z, z squared up to z to the k, these are normalizable. But not beyond. Okay, so the different k's corresponding to the different line bundles give me very different spaces of states. K plus one-dimensional spaces of states. In fancier cases, I couldn't just stereographically project to the complex plane, and I really need to work with line bundles. I'm stereographically projecting here to make it easy for people who don't know about line bundles to follow what I'm doing. Now, final exercise. Define the following operators. Ji is j plus 1 qk of xi, where j is equal to k over 2. What's xi? Well, think of this 2-sphere, which we stereographically projected, as sitting inside R3. R3 has coordinates x1, x2, x3. You can restrict those coordinates to S2, and you get a function on S2. So that's xi's are functions on S2. Quantize those. Here's the exercise. Compute j sub I, j sub j equals square root of minus 1, epsilon I j k, j sub k. All right? What we learn is that this h sub k is a representation of SU2. Actually, just of its Lie algebra, but it exponentiates. In fact, these are eigenstates. These guys here are eigenstates of J3. Now, it's not obvious from what I said, but it turns out that h sub k is isomorphic to the irreducible representation of SU2 of spin j equals k over 2. So can I take 2 minutes? I want to make a point that fits in very well here. Thank you. Yeah, I'm wrapping up. Now, it's interesting to think, so what's the dimension of this space, everybody? What's the dimension of HK? Oh, you're all in a state of shock. K plus 1, yes, thank you. Right, okay. So the exact dimension of h sub k is k plus 1. Now remember the Bohr-Summerfeld rule is that for each unit of phase space area we should get a quantum state in the semi-classical limit. So the integral of omega over 2 pi of CP1 is 1. So if I take omega to the k, it's k. So Bohr-Summerfeld would have predicted that I get a k-dimensional space of states. But I got k plus 1. Well, this is k times 1 plus h bar, because h bar is 1 over k. Okay? So this plus 1 is a quantum correction to what we expect from Bohr-Summerfeld. And now here's the final remark. In general, if L is sufficiently positive, then the dimension, the complex dimension of H0 of P valued in L tensor K is the sum of -1 to the I, the dimension of the other cohomology groups. This goes from I equals 0 to whatever it has to go. L tensor K. And is this movable? Good. This thing here is known as an index, d bar sub L. And it's exactly the kind of index that Clay was talking about. You can form the supersymmetric quantum mechanics where this is literally the Witten index. And there's an index theorem that says that this is e to the k C1 of L times a characteristic class called the Tud class of P. And so this is equal to k to the dimension of P over 2 times the symplectic volume times 1 plus order 1 over k corrections. And so what you see is that curvature either adds or subtracts quantum states. The curvature of the phase space adds or subtracts quantum states. The sign of the curvature is what's going to determine whether you add or subtract. This whole thing is what I've been telling you for SU2 is a special case of a very beautiful general statement about representations of compact Lie groups called the Borel-Weil-Bott theorem, which plays a very important role when discussing Wilson line defects and insertions of punctures in Chern-Simons theory. We won't get to the details of that, unfortunately, but what I'm telling you is just the tip of a very beautiful iceberg of mathematics for how to think about representations of Lie groups. It's called geometric representation theory. So thank you.
Maybe one quick question? If not, we can go refuel at lunch, and I'll see you all at 2 o'clock.